In section 9.1, we look at algebra and composition of functions. So first we will just look at the basic operations on functions. And so the basic idea here is that you can add, subtract, multiply, and divide two functions. And when you do that, you get a new function. And so here's the notation that we use. We call the function f plus g of x the function that you get when you add the functions f of x and g of x together. So f and g are two separate functions. When you add them together, you get a new function, and the name we give that function is f plus g. And this is called the sum function. Sum, of course, meaning that we added the functions together. The function f minus g of x comes from subtracting the functions f and g, and this is called the difference function. The function f times g of x comes from multiplying the functions f and g together, and this is what we call the product function. And finally, the function f over g of x is defined to be f of x divided by g of x. And when we do this, of course, g of x cannot be 0 because we are not allowed to divide by 0. And this function is called the quotient function. And as a note here, the domain of each of these functions is the set of all x that are in the domain of f and the domain of g. So in other words, the domain of each of these four functions would consist of all x values that belong to both domains of the original functions. Let's take a look at some examples. So here we have the function f of x equals 3x plus 2, and the function g of x equals x minus 5. And as a note, I'm going to mention that the domain of f of x is all real numbers because there are no values of x that we are not allowed to plug in. And the domain of g of x is also all real numbers because, once again, there are no restrictions here. So let's go ahead and find the following functions. First, I would like to compute the function f plus g of x. And keep in mind that this is defined to be f of x plus g of x. And we know that f of x is 3x plus 2, and g of x is x minus 5. And we are simply taking these two functions and adding them together to get the sum function. And if you combine like terms here, you end up getting 4x minus 3. And the domain of this function would be all real numbers because the domain of each of the original functions was all real numbers. Next up, we're looking for the function g plus f of x. Notice that it's kind of like this function, except that we have reversed the order here. So g plus f would be g of x plus f of x, and g of x we know is x plus 5, and f of x we know is 3x plus 2. And when you combine like terms, you get 4x minus 3, and its domain is also all real numbers. And of course, it is no coincidence that these two are the same. And that is because when you are adding two functions together, it doesn't matter which one comes first or which one comes second. And so right down below here, I'm just going to remind you that f plus g of x is the same as g plus f of x. And this is true for any two functions, f and g. In the next example, we would like to compute f minus g of x. And so, again, this would be f of x minus g of x by the definition. And f of x is 3x plus 2. And when I subtract g of x is x minus 5, but I need to put parentheses around that. And this is because when you subtract something, you have to distribute the negative here. And so this ends up being 3x plus 2 minus x plus 5, which is 2x plus 7. And the domain of this, of course, is all real numbers. Now for our next one, we want to do g minus f of x, which would be defined as g of x minus f of x. G of x is x minus 5. And when you subtract f of x, you need to put parentheses around f of x. And again, this is because we need to distribute. And if we do the math here, we have x minus 5 minus 3x minus 2, which is negative 2x minus 7. And the domain here is all real numbers. And of course, I want you to realize here that f minus g and g minus f are not the same. They're different. And in fact, they are opposites of each other, aren't they? Right? 2x plus 7 is the opposite of negative 2x minus 7. And so I'm going to write down that f minus g of x is the opposite of g minus f of x. So most important thing here is to realize that they are not the same. Okay, moving on down the list here. Next step, what I want to find is the function f times g of x. And to do f times g, this will be equal to f of x, which is 3x plus 2, multiplied by g of x, which is x minus 5. And because we're multiplying, I like to put both functions in parentheses. And this is very functional, pardon the pun. But we're going to FOIL here. And this gives us 3x squared minus 15x plus 2x minus 10, which is 3x squared minus 13x minus 10. And the domain of this function is, once again, all real numbers. So what I hope you're seeing from these examples is that adding, subtracting, multiplying functions, this is all stuff that you've done before. So the only thing that's really new here is this notation. You have to get used to this notation, which is telling you what to do. So for the last two functions here, I want to find the function f over g of x, and then finally g over f of x. Well, f over g is simply f of x divided by g of x. And this is equal to f of x is 3x plus 2 divided by g of x is x minus 5. And this is the result. We're going to leave it like this. And the domain here, you have to be a little bit careful. Again, the two original domains were all real numbers. And so the domain here would be all real numbers. However, as you know, you cannot divide by 0. So in this case, x cannot be equal to 5 because 5 minus 5 would be 0. So the domain is all numbers except for 5. And the way we write this is by using interval notation. So we'll take the domain to be all the numbers from negative infinity up to 5, union all the numbers from 5 to infinity. And finally, we have g over f of x, which is simply g of x divided by f of x. And this would be x minus 5 divided by 3x plus 2. And again, the main point here is that these two functions are not the same. So when you divide, the order matters. And of course, its domain is also not the same. In this case, the domain can be every number except for the number that makes this denominator 0. Now, some of you may be able to look at this and say, well, I know that x can't be negative 2/3. But if you can't see that, what you do is you take that denominator and you set it equal to 0, and you solve this corresponding equation. And this is how you find that negative 2/3 is the number that makes the denominator 0. Therefore, negative 2/3 is the number that needs to be excluded from the domain. So these are just basic function operations: adding, subtracting, multiplying, and dividing. And a couple of takeaways from here is that when you subtract, you have to be careful because the order matters. And also when you divide, you have to be careful because, once again, the order matters. Okay, so just a couple more examples here. In this example, s of x is the function x squared minus 5x, and t of x is the function 3x plus 8. And the first thing I want to do here is find s times t of x. And so by definition, s times t of x is s of x times t of x. And s of x is x squared minus 5x. And we're going to multiply that by t of x, which is 3x plus 8. And if we FOIL here, we will end up with 3x cubed plus 8x squared minus 15x squared, and finally minus 40x. And if we combine like terms here in the middle, we end up getting 3x cubed minus 7x squared minus 40x. And again, this is the function s times t of x. Okay, so that is our answer here. All right, now for the second example, we want to find s times t of 1. So that means we want to plug in the value x equals 1 into the function s times t. Well, the function s times t is right here. This is s times t of x. So if x equals 1, all we have to do is plug in 1 into that function. And so because we just figured s times t, just because we just figured that out, what we can do here is we can simply take x equals 1 and plug it into this function. And that's going to give us 3 times 1 cubed minus 7 times 1 squared minus 40 times 1. And if you do the math here, 1 cubed is 1, so you get 3 minus 1 squared is 1 times 7 is 7, so minus 7. And then minus 40 times 1 is 40. And this ends up being negative 44. And so that is the value s times t of 1. Now what I want to show you here is that there is an alternative way to figure this out. And it goes something like this. S times t of 1 is the same as s of 1 times t of 1. Because again, this is just the definition of what it means to take the product function. So what you can do is you can figure out s of 1 and t of 1 separately and then plug those in. So let me show you what this would look like. Let's go off to the side here. S of 1 would be taking s of x and plugging x equals 1 into that function. And so if we do that, we get 1 squared minus 5 times 1, and that is negative 4. And t of 1 is very similar. to do t of 1, we're going to plug x equals 1 into the t function. And if you plug in 1 here, you get 3 times 1 plus 8. And 3 times 1 plus 8 is 11. And so we now know that s of 1 is negative 4 and t of 1 is 11. And so s of 1 times t of 1 is negative 4 times 11, which is negative 44. And so notice you get the same answer. And so I'm not saying that one method is better than the other. I'm saying that you have a choice. You can do it 2 different ways. All right, for our next example, we would like to find t divided by s of x, t divided by s of x. So we know by definition this is t of x divided by s of x. And we know that t of x is 3x plus 8 divided by s of x is x squared minus 5x. And you could leave it like this. However, I'm going to simplify the denominator by factoring. So we know that x squared minus 5x is x times x minus 5. And the reason I'm doing this is because once you factor it, it's really clear that x cannot equal 0 and also x cannot equal 5, because plugging in these numbers will make one of those factors 0, which makes the entire denominator 0. So again, I'm getting back to domain here. And so you can express the answer either way. Either way is fine. But if you have to give the domain, this is more useful. And so the domain would be all numbers except for 0 and 5. So that would be all numbers from minus infinity to 0, union the numbers from 0 to 5, union the numbers from 5 to infinity. And if you're having a hard time understanding what I'm doing here, look at a number line. Here's 0 and here's 5. So we're saying that x can equal any number except for those two numbers. So you have numbers here, you have numbers here, or you have numbers here. And that's what these 3 intervals represent. Okay, and finally, let's do t over s of 4. And so one way to do t over s of 4, since we just found t over s of x, which is this function, what we could do is just take x equals 4 and plug it into this function. And if you do it that way, you get 3 times 4 plus 8 divided by 4 squared minus 5 times 4. Do the math. This is 12 plus 8 divided by 16 minus 20, which is 20 divided by negative 4, which is negative 5. Okay, so this is one way to do it. And then as an alternative, we could use the definition. T over s of 4 is the same as t of 4 divided by s of 4. And then, of course, you would have to figure out what is t of 4 and what is s of 4. And you'd plug those in, and of course, you would end up getting the same thing, 20 divided by negative 4, which is negative 5. Okay, so either method is fine. All right, and it is a little weird, isn't it, to talk about functions s of x and t of x. We're not really used to those letters for functions. You know, usually we like to talk about f and g. Well, sometimes you'll see different letters besides f and g, and so it's good to get used to that. Okay, next up we want to talk about compositions of functions. So the composition function, which is written like this, f of g, is defined by taking one function and plugging it into the other. Okay, so it's another way to combine two functions together, except that we're not adding, subtracting, multiplying, or dividing. you're actually plugging one function into the other one. So I'll show you an example of this in just a minute, but first I'd like to start with, what does this mean? Let me show you a function map. So I'm going to start here with a set of numbers, and I'm going to pick one of those numbers, which I'm going to call an x value. And what happens when you plug an x value into this function here? What happens to that x value is you first apply the function g to that x value. So g is a rule, it's going to do something to that x value. Whatever it does, when you take g and you apply it to that x value, that's going to convert it into a new value. So the function g will take that x value and it will send it to a new value, which we will call g of x. And that's in this set of numbers. And so g is what did this. Then what happens is you take this number, this g of x, and now you apply the function f to it. And that function f is going to take this value and it's going to bring it to a new value. And so f will now take that g of x value and it will turn it into a f of g of x value. So what a composition function does is it applies two functions to a particular value of x in succession. Okay? And the actual composition itself, what it does is it gives you a shortcut to go from this value to this value, bypassing the value in the middle. And this is the function that we call the composition of f and g. Okay? So the composition of two functions is a shortcut so that you don't have to plug a value into one function and then take that value and plug it into another function. And I'll give you some examples, a concrete example here in just a second. So one last thing before we go to the next slide here is that this is the technical notation for composition. This little circle here looks like the word fog. It's not the word fog. This is a little circle that stands for composition. And this is what it means. It means you're plugging one function, the second function, into the first function. Okay, so this is not multiplication. You're plugging one function into the other one. Let's do an example. So here's a function f of x equals 5x minus 3, and g of x equals x squared plus 4. And what I want to do first is the composition of f and g, which means, again, by definition, it means we are doing this, f of g of x. So we are plugging g of x into f of x. Now, some people can do this very quickly. They understand what it means. If you don't understand what it means right away, then what I would recommend doing is starting by replacing g of x with what you know it is equal to. So you don't start on the outside, you start on the inside. We know g of x is the function x squared plus 4. So we can take x squared plus 4 and we can replace g of x with that. And if we do that, we get f of x squared plus 4. Now, how do we do f of x squared plus 4? Well, go to your definition for f. F of x says that you take any x value that you get, and what you do is you multiply that x value by 5, and then you subtract 3. Well, this is the value that we get. So we're going to take this value, multiply it by 5, and subtract 3. And so when we do that, we get 5 times x squared plus 4 minus 3. And if we do the math on this, this is 5x squared plus 20 minus 3. And this is 5x squared plus 17. All right, so this is our final answer here. Okay, Let's try the second example. The second example says same functions, but now I want to do the composition of g and f. And what this does is it reverses the order. And so by definition, this means you are going to take the function f of x and plug it into the function g of x. So it's backwards, right? In example number 1, we took this function and we plugged it into here. In this example, we're going to take this function and plug it into here. And so we can go step by step. By definition, this is equal to g of whatever f of x is, and f of x is 5x minus 3. And then how do we do g of anything? Well, the rule is right here. G of any number x is that number squared plus 4. So if I'm doing g of 5x minus 3, I have to take that number, 5x minus 3. I have to square it and then add 4. Okay? Now we have to work that out. So this is 5x minus 3 times 5x minus 3 plus 4. And then, of course, FOIL. And so this is 25x squared minus 15x plus 9 plus 4. And this finally ends up as 25x squared minus 30x plus 13. And again, this is our composition g of f of x. So same two functions, but in the reverse order. And of course, one thing I want to point out is that these two functions are not the same. So when you do a composition, the order matters. F of g of x is not going to be the same as g of f of x. All right, so next up, what I want to do is I want to look at f of g of 2. F of g of 2, what is that? Well, let's remind ourselves that for this example, f of x was the function 5x minus 3, and g of x is the function x squared plus 4. And when we're doing f of g of 2, this is the same as doing g of 2 and then plugging that into f. So this is the more useful notation. These are the same, but this is more useful. Now, there's two ways we can do this. One way to do it is to just work out the inside first. So you could say, well, what is g of 2? Well, here's our g function. G of 2 means to plug 2 in for x. So this would just be 2 squared plus 4, which is 4 plus 4, which is 8. Now, once we know that g of 2 is equal to 8, then this original problem simply becomes f of 8, because again, we know g of 2 is 8. And then f of 8, well, you plug that into your f function, right? So f of 8 is, by definition here, 5 times 8 minus 3, which is 40, minus 3, which is 37. And so we can figure out that the value is 37 by doing this sequentially, right? So what I mean by sequentially is first we take 2 and plug it into g. That gives us 8. Then we take 8 and plug it into f, and that gives us 37. And so let me illustrate what we did here. We had an original set, original domain x. We picked the number x equals 2. The function g took that number x equals 2, and it turned it into a new number, which was x equals 8. Okay, that's what the function g did. And then the function f took that number 8 and turned it into 37. And so the function f took 8 and turned it into 37. Okay, that's what happened. Again, this is G and this is F. All right, now there's a shortcut to doing this. There is a function that will take the number 2 straight to the number 37. And this function is the function f of g. And we know what that function f of g is because we figured it out up here, right? Here's f of g. It's right there. It's 5x squared plus 17. So let's bring that down. If f of g of x is 5x squared plus 17, then we can go back to this original problem now. And if we want f of g of 2, all we have to do is plug the number 2 into here. And that would give us 5 times 2 squared plus 17. This is 20 plus 17, which is 37. So again, same result. Right? This gives us the same result. So there's 2 ways to do it, and this is what a composition is all about. I recommend that you know both ways. They're both good. All right, in section 9.2, we're going to introduce the concept of inverse functions. And I'm going to give a really simple example of what an inverse does. So let's suppose you have some function f, some very simple function f. And f takes the number x equals 1 and it turns it into the number y equals 8. And x equals 3 turns into y equals 4. X equals 4 turns into y equals 10. And x equals 7 turns into y equals 2. So just imagine that there's some function that does that to those 4 particular x values. The idea of an inverse function is that it reverses the process. So it will undo what the function did. So the inverse of this function f would take these numbers, 8, 4, 10, and 2, and it would send it back to where it came from. So the number 8, right? So this would be x equals 8 now, turns into the number y equals 1. X equals 4 turns into y equals 3, etc. So we need a function that will do this because, as you know, just from working with computers, etc., undoing things is very important. Of course, you want to be able to do things, but when you make a mistake, you want to be able to undo those things. So, first thing I'm going to do here is talk about the function f of x equals 3x minus 2 and how we can find the inverse of this function. So if you go back to this very basic concept, the basic idea is a function takes a set of x's and it converts it into y's. And the inverse is going to take those y's and convert it back into x. So the roles of these functions is that x and y are reversed. Okay? So the first thing you need to do when you want to find the inverse of a function is you need to invert the roles of x and y. So here's how it goes. We're going to start with our function f of x equals 3x minus 2, and we're going to express it using y notation. Okay? So we're going to go back to the simpler notation, y equals 3x minus 2. Again, this is our original function. The inverse of this function occurs when you switch x and y. And the fancy word for switch is to invert, and that's why it's called the inverse function. So y is going to become x, and x is going to become y. And when you do that, you get x equals 3y minus 2. And this is the inversion process. In other words, this is the critical step when you're finding the inverse function. Now, what we need to do to find this sort of new function is we need to solve for the new y. So now what we're going to do is just add 2 to both sides. That gives us x plus 2 is equal to 3y. And then we'll divide both sides by 3. And that gives us x plus 2 over 3 is equal to y. And then we're going to just rewrite it by reversing both sides here. So we want it to say y equals. And this equation right here, this is our inverse. So we started with the function f of x equals 3x minus 2, and we figured out by switching x and y and solving for the new y here, we figured out that this equation gives us our so-called inverse. So the last consideration here is, how should we notate this? What notation should we use to write this? Well, since this is the new inverse, we're going to rename y using function notation, but it's the inverse, and so we're going to call it f inverse of x, and we use that little -1 to indicate this. Okay, so this is our inverse function, and this little -1 right here kind of looks like an exponent, but it's not an exponent. It's inverse notation. Okay, so this is inverse function notation. Okay, but again, the procedure is very simple. Let's summarize it. So let's talk about the process for finding f inverse of x. So first of all, we're going to rename f of x with y. In other words, we take our original function f of x and we replace f of x with y. The second step is you switch x and y. And then you solve for the so-called new y. And that new y is your inverse, and then you name your new y as f inverse of x. That's the basic procedure for finding an inverse. Let's try another example. So in this example, we have a function g of x, which is equal to x squared minus 3, and I want to find the inverse of this g of x. Okay? So the steps are really simple. We start with our original equation, g of x equals x squared minus 3. We're going to rename g of x as y, and the reason we do this is because y is just a simpler notation. Next, to find the inverse, we switch x and y. So y becomes x, and x becomes y. And then we solve for our new y. Our new y is right here. Now we have to solve for that y. So I'm going to add 3 to both sides. That will give us x plus 3 is equal to y squared. And then you guys know the drill. We're going to take the square root of both sides. Now when you take the square root of y squared, you get the absolute value of y. And if I reverse sides here, we get this. And then finally, if the absolute value of y equals radical x plus 3, this means y equals plus or minus radical x plus 3. And so this is our inverse. However, there's something really important happening here. This is our inverse, but this equation is not a function. We didn't have that problem in our last example. It's not a function because, for example, let me make a little table of values here. So let's take the equation y equals plus or minus the square root of x plus 3. And let me just substitute a couple of values into this function. What if x is equal to 1? What is y equal to if x is equal to 1? Do the math. Y would be equal to plus or minus the square root of 1 plus 3, which would be plus or minus the square root of 4, which would be plus or minus 2. Now remember, that's two different values. So that's saying that y equals 2 or y equals negative 2. So when x equals 1, y could equal 2, or when x equals 1, y could equal negative 2. This can't happen in a function. This can't happen. So we have a problem here, right? We have a clear problem here. The problem is that our original function was not the right kind of function to have an inverse that was also a function. Let me just kind of show you what I mean by this. If you graph g of x equals x squared minus 3, and if you graph y equals plus or minus the square root of x plus 3, here is what you get. So the graph of g of x is a parabola. G of x equals x squared minus 3. And the graph of y equals positive or negative square root of x plus 3 is this graph right here. Now, what we saw is that when you plug in x equals 1, you get 2 or you get negative 2. I can show you this on the graph. This happens right here. When x equals 1, you can see that you get two separate values of y. You get y equals 2, and you get y equals negative 2. That's a problem, because remember, to have a function, a vertical line cannot hit the graph twice. It's been a while since we've talked about that, but if you have a function, a vertical line cannot hit the graph twice. Well, look, these graphs are related. These are inverses of each other. So you should see that there is a certain type of symmetry between the original function g of x and this inverse, which is this sideways parabola here. Now, the relationship is really simple. If you go back to the original function, you can see that this horizontal line, y equals 1, has two separate values of x that correspond to it. Well, when you invert, when you switch the roles of x and y, the y values become the x values and the x values become the y values. So the short of this is the following. If a horizontal line hits your original function more than once, then when you do your inverse, a vertical line is going to hit that more than once, which means it won't be a function. So how do we avoid this? We avoid this by saying in our original function, horizontal lines cannot hit the graph more than once. And this function has a name. It's called a one-to-one function. And so the idea is very simple. A function f of x has to be a one-to-one function in order for its inverse to also be a function. What is the definition of a one-to-one function? Here it is. A function is a one-to-one function if each x value corresponds to exactly one y value and each y value corresponds to exactly one x value. Thus the name one-to-one. One x corresponds to one y and one y corresponds to one x. The way you test for this in its simplest form is by using something called the horizontal line test, which simply says a function is one-to-one if each horizontal line intersects its graph at most one time. Let me show you some examples. Let's consider the following three functions. So we'll start with the first one here, which is f of x equals 1/2 x plus 1. this is the graph of a line, and this graph will look like this. And I'm not going to go through and remind you all about how to graph lines, but this is what f of x will look like. Notice that this function is one-to-one, because if you imagine drawing horizontal lines, every horizontal line that you could possibly draw is only going to hit that graph one time. Okay, so if you want, I can come in here and I can sketch a few. Here's some horizontal lines. And again, you can imagine if you drew every possible horizontal line, it's only going to intersect the graph once. And so we're going to say f of x is one-to-one. Okay, and the abbreviation for one-to-one is 1-1. Okay. Now, the next function, g of x, right, this one here, is x squared minus 1. This is a parabola. And if you were to graph this parabola, and again, I'm going to skip the details here, but if you graph this parabola, you would get the following graph. And this function, it is a function, but it is clearly not one-to-one, because you can see very easily, if you draw a horizontal line, you are going to hit the graph more than once. And in fact, just about every horizontal line you draw hits the graph more than once. So g of x is not one-to-one. And again, the significance of that is that the inverse of g of x will not be a function. And finally, h of x equals the absolute value of x. I just threw this one in there for some fun. The absolute value of x is a relatively simple graph. It looks something like this. And this is once again an example of a function that is not one-to-one, because horizontal lines are hitting the graph more than once. So h of x is not one-to-one. Okay? So it's pretty easy to identify when you have a one-to-one function if you have the graph of that function. Let's go back and talk about some more inverse stuff. So here's a function, f of x equals the cube root of x plus 1, and I would like to find its inverse function. And I will just note real quick that this function, f of x equals the cube root of x plus 1, is a one-to-one function. In fact, I'll even graph it for you to show you what it looks like. Okay, so here is a rough sketch of what the function cube root of x plus 1 looks like. And you can see that if you draw horizontal lines, they are only going to hit that graph one time. Okay, so it is a one-to-one function. Now, let's not worry about the one-to-one part right now. Instead, what I want to focus on here is how do we find the inverse? Let's go through the steps again. So the first thing you do when you're looking for the inverse of a function, first thing you do is you change f of x to the variable y, because it's easier to deal with. Then you are going to switch x and y, so y becomes x and x becomes y. And then we take that new equation and we have to solve for y. So think about this for a minute. To solve for y, we have to get rid of this cube root. And the way we get rid of a cube root is by cubing both sides. So what I'm going to do is raise the left side to the third power, raise the right side to the third power. This gives us x cubed is equal to y plus 1. And one last step here, I'm going to subtract 1 from both sides. So we get x cubed minus 1 is equal to y. And this is our inverse. And we know this inverse is a function because our original function was one-to-one. So we can go ahead and rewrite the inverse using inverse function notation. So instead of writing y equals x cubed minus 1, I'm going to write f inverse of x equals x cubed minus 1. And this is our inverse function. Now, one last thing I'd like to talk about here is what an actual inverse function does. So this is a perfect example. We had f of x was the cube root of x plus 1, and we had the inverse function f inverse of x equals x cubed minus 1. And what an inverse function does is it reverses the roles of x and y. So, for example, if x equals 7 here, then f of 7 would be the cube root of 7 plus 1, which is the cube root of 8, which is 2. And so we can see that f of 7 is equal to 2. So if this is truly the inverse of this function, it should reverse the roles of x and y. Okay, so this goes with the function. Now let's look at the inverse. So for the inverse, what if I let x equal 2? What would x equal 2 give us? Well, the inverse function evaluated at 2 would just be plugging 2 into here. And that is 2 cubed minus 1, which is 8 minus 1, which is 7. And so we can see f inverse of 2 is equal to 7. And that is exactly what should happen, right? So look at what the inverse did. The original function takes the number 7 and gives you the number 2. The inverse function takes the number 2 and gives you the number 7. So it inverses or inverts the roles of x and y. One final concept here. This is a property of inverse functions. And the property says that if you have two inverse functions, f of x and f inverse of x, when you do the compositions of the two functions in either order, you should get x for both of those. Okay, so here's an example. We have a function f of x equals 5x minus 3. I have another function g of x equals x plus 3 divided by 5. And I want to show that these functions are inverses of each other. And the way we show that they are inverses is by doing the composition both ways and showing that you get x each time. So let's take a look at how this would work. So first, let's compute f of g of x, which means you're taking the function g of x and plugging it into the function f of x. And this would be f of g of x is x plus 3 divided by 5. And so we're going to take x plus 3 divided by 5, and we're going to plug it into the function f. And so this gives us 5 times x plus 3 divided by 5 minus 3. And if we do the math, the 5's cancel, and we get x plus 3 minus 3, which is x. So check that. That's good, right? That's what we were supposed to have happen. But to be inverses, this also needs to be true. So if I reverse the composition, I have to get the same thing. So next I need to check to make sure that g of f of x is also equal to x. And so to do this, we're going to plug the function f of x into g of x, and f of x is 5x minus 3. And we are going to take 5x minus 3 and plug it into here. And so that becomes 5x minus 3 plus 3 divided by 5. Cancel, and we get 5x divided by 5, and those 5's cancel, and we end up getting just x. So because both compositions, both ways, both gave us x, we can say, therefore, f of x and g of x are inverses of each other. All right, this was a long one, but we're done.